mark at. Okay. All right. Every polynomial of degree n has exactly n roots or n solutions. And here's the part. That only works out if we say that some of those roots can be real and some of them can be imaginary. So, when we say n roots, we mean n complex roots, okay? Because they can be either real or imaginary, right? And then that second piece says, well, if it has those roots, then it can be written in this form, which is truly amazing. You can write it in factored form, okay? So every single polynomial can be written in factored form. X minus the first root, x minus the second root, x minus the third root, and x minus the last root. Now, it's also true that as we factor it, there may be the need to have a coefficient out front in order to generate that new polynomial. But every polynomial can be written in that form. And then there's one other piece to this fundamental theorem of algebra that is really cool. And it says if a polynomial p of x has a solution of a plus bi, we talked about it yesterday, can imaginary solutions ever happen by themselves? Just one of them. No, they always come in pairs. So if a minus bi is a solution, then another solution must be a minus bi, or the conjugate. That will always be the case. So we're going to apply our knowledge about the fundamental theorem of algebra to some problems right now. We're going to identify the total number of possible real, we'll say positive real. I'm going to switch it a little bit from the directions I did last year. So I did kind of some investigating here. This is going to be the better way to teach it. We're going to go positive real. We're going to go negative real. We're going to go total real. We're going to go imaginary. And then we're going to go to our choices for the rational root theorem if we were to use it. Then we're going to find our actual solutions. So A for the day, which student out there can tell me how I identify the number of positive real solutions this is going to have? There is one positive real solution. Why? We look at the sign change. So you guys, if you can do that on a test, you can get some free points. All right. How do I figure out the number of negative real? And if I switch it to negative x, does the equation change? And how many sign changes will that have? 1. So think about what we've stated. Question. There's nowhere to plug the x in for. So if it was a negative 16x and you plugged in a negative x, then you would get 16x. But there's no x here to plug it in for, so it just stays the same. Better? Good question. Thank you for asking. Now, notice what we've said. It for sure has one positive real. It for sure has one negative real. So how many total real does it have? Is it possible it only has 0? No. It has one positive. It has one negative. It has how many total real? For sure 2. So if it has 2 real, how many total does it have? So therefore, how many imaginary? Okay. Yes. Look at your degree. The fundamental theorem of algebra says this has how many solutions? And how many real do we have? So how many imaginary must there be? Yeah. So look at what we've said. We have not even found any solution. And from the outset, we've said, I know what my answer is going to be. We're going to get one result that's positive, one that's negative, and 2 that's imaginary. What a great way to check our answer. Let's see if it works out. Our choices would be plus or minus 1, plus minus 2, plus minus 4, 8/16. So Descartes is the one who made great advances in being able to understand the nature of solutions. Okay, he didn't put together the formulated fundamental theorem of algebra. By the way, do you guys know what we call this? We call that the coordinate plane, right? Have you ever heard of it called the Cartesian plane? Cartesian after Descartes. So that's why we call it the Cartesian plane, if you hear that. So, would you like to use the rational root theorem, or would you like to factor this? Factor it. So 0 equals. How does it factor? Yeah, good. Well, that factors, doesn't it? So what are two of my solutions? Look at that. We got 2 and -2. Do we find the positive and the negative real solutions? Yeah, but we know we're going to have 2 imaginary. They're going to come from right here. X squared plus 4 is equal to 0. So x squared equals 4. -4, excuse me. What's the square root of -4? Plus or minus 2i. We have 1 positive real, 1 negative real, and exactly 2 imaginary. Already done for us. If you can't think that that's somehow at least a little bit cool, I've got nothing else for you. I think that that's one of the coolest things you're going to see. I think it's amazing. All right, it's pretty awesome. All right, let's see it happen again. Goodbye. Positive real. Positive real. 0. Negative real. This is going to switch to a negative 8x cubed plus 1, right? So that's 1. So how many total real will there be? There'll be 1 total real solutions. How many total solutions are there altogether? 3. So if there's... Very good. Can this number here ever be odd? Why? Because they always come in pairs. You guys are geniuses. We got 1 and 1. We've got 1, 2, 4, and 8. So what are my choices? Half, because it's p's divided by q's. So it's the back divided by the front. So 1 over 1, 1 over 2, 1 over 4, and 1 over 8. Jackson, do you see that? If it was switched around, if it was x cubed plus 8, then it would be plus minus 1, plus minus 2, 4, 8. Better? Okay, does that factor? Cubes. Very good. Sum of cubes. What's the cube root of 8x cubed? 2x. Square in the front. Square in the back. Multiply the 2 together. Opposite sign. If you don't remember the factoring of the sum of cubes or difference of cubes, I handed to you a sheet at the beginning of this unit. It was a graphic organizer, and on there is the list of all of your factoring options. That's something you can keep on hand. But that's how we factor the sum and difference of cubes. Okay. So what's my solution here? -1/2. Was that one of my choices? Yep, it's a rational solution, so it should show up as one of my choices, and that's my negative real, isn't it? So I need 2 imaginary. Can I factor that? No, I can't. So what do I use? Quadratic formula. 2 plus or minus square root of what? 4 minus 4 times 1 all over 2a, or 8. We call the part underneath the square root a discriminant because it discriminates the result. It tells us the difference between the results. What is the value of the discriminant? -12. What can you factor out of a -12? -4 and +3. What's the square root of -4? 2i, roots of 3 all over 8. What are those divisible by? 2. And if I divide them by 2, I get 1 plus or minus I roots of 3 over 4. Once again, we have no positive real solutions. We have one negative real solution. We have 2 imaginary solutions, and our rational solution was one of our choices. So a great way to verify your answer. All done before we even start. Okay. All right, last hefty example, then we go to 2 that are a little bit easier. You're going to get about 15 minutes for work time today. And again, a worksheet, not a book assignment. I would have worksheets for you for the entire rest of the year if I could, but I'm doing that for calculus. That way, those of you who are juniors, next year when we take calculus, I believe you won't have a book assignment the entire year. I'll have specially designed worksheets for every assignment for you. And then next year I'll work on college algebra and trig. Trig has a lot more worksheets. Positive real, how many sign changes? 3. Okay, but for 1, okay, before when I came up with 1, you can't subtract 2, okay, you can't go negative, so. Negative real, I got to plug in a negative x, and I get negative 2x cubed minus 13x squared minus 26x minus 10. How many sign changes are there? There's none of them. So how many real do I have? 3 or 1? Because you have 3 and 0 or 1 and 0. So suppose I had 3 real roots. How many imaginary would there be? None. Suppose I had 1 real root. How many imaginary would there be? 2. Is everybody clear on that? Because that is a point of confusion when people go to the test. Like, how did you come up with the imaginary? These have to add up to what? 3. That's a fundamental theorem of algebra. Okay? Choices. Oh boy. Yeah. All right, let's get on our positive mental attitude. We got 1 and 2. We got 1, 2, 5, and 10. Somebody help me out. Good. A half. 5 halves. Would it be great if we could eliminate some of those? Which ones can you eliminate? Why? We know that there's no negative solutions, folks. Let's use that information. So if we plug in 1, 1 doesn't work. But everybody then says, we'll try negative 1. It ain't gonna work. You agree? You plug in 2. We already tried it in the last class. 2 doesn't work. We tried 5. 5 doesn't work. Let's try a half. See if half works. What's 1 half cubed? 1/8 times 2. 1/4. What's 1 half squared? 1/4 times negative 13 is negative 13/4. 26 times a half? 13, or 52/4. Minus 10, 40/4. 1 minus 13, negative 12 plus 52, 40 plus, or minus 40. Hey, 1 half works, so x minus 1 half is a factor. So let's run the 1 half through in the synthetic division. Two, 1. Negative 12, negative 6, 20, 10, 0. So x minus 1 half times 2x squared minus 12x plus 20. Does that factor? What could I take out of this? Take a 2. I get x squared minus 6x plus 10. Does that factor? Are there two numbers that multiply to positive 10 to add a negative 6? There are not. And we already know, okay, from our work here, that we came up with one positive real, that we could very well come up with two imaginary. So the fact is, using the quadratic formula is an option that might come up. 6 plus or minus the square root of minus 4 times 1 times 10, all divided by dose. 6 plus or minus. Okay, so Will's already through that. He did 36 minus 40 is negative 4, and the square root of negative 4 is 2i divided by 2 and my original solution was 1/2. As we check our work, sure enough, we have one positive real, we have none that are negative, we have two imaginary. The one that was a rational solution is sitting right there for us. Great way to check our work and verify. Any questions on that before we move on to the second part? Going once, twice, 3 times whole. Okay, now what we want to do is we want to go the opposite direction. Here's the solutions. Write a polynomial. Is it possible for a polynomial to have a solution of just 4 and I? That would mean I have just one imaginary solution, doesn't it? We need 2. And if I is a solution, so is its conjugate. What is the conjugate of I? Negative I. So negative I is also a solution. Well, the fundamental theorem of algebra told us that this can be written in factored form. Every single polynomial can be written in factored form. I just do x minus the solution, x minus the solution, x minus the solution. We want to multiply this together and get our polynomial. So I have x minus 4 times x minus I times x plus I. What would you like to focus on multiplying first? Good choice. Let's multiply those imaginary parts first. They are conjugates, aren't they? And what happens when we multiply conjugates? The middles go away. So we get x squared, and then there's a negative I squared. What's negative I squared? Positive 1. Does it make sense to you that x squared plus 1 produces roots of positive I and negative I? That's a good way to check to make sure that we're on the right track before we move forward. Should we now multiply those out? Let's do it. P of x is equal to x cubed minus 4x squared plus 4x minus 4. No big deal, huh? I write it as x minus from the beginning. I multiply it out. Notice that my imaginary parts went away. Will? Whoops, sorry. Thank you. Thank you. Sorry. Absolutely right. Should not be a 4x, but rather just x. Thank you. Okay, good. They're not perfect either. It was very satisfying being a teacher, be like, oh, hey, don't worry, you missed a negative sign there, you know. Happens there. That's it. That's it. That's the polynomial. It says find a polynomial. Yeah. No big deal, right? Yeah, I hear you. You get tired? Cold tired? Oh, okay. I would get tired. 6 hours is my worst. Oh, gosh. Try to make it through 6 hours. All right, last one. You ready to dig in? If 4 minus 2i roots of 3 is a solution, What's the other one? Very good. So I'm not going to skip any steps here. I'm going to write it all out. X minus negative 3. You can. I'm just doing it for teaching effect. But without a doubt, I would write x plus 3. But Jackson, here's where I'd be especially careful. X minus the quantity for minus 2i roots of 3. A lot of people will get the negative miss there. And then this one, x minus 4 plus 2i roots of 3. But here's what a lot of people do, Jackson. They write x minus here, and they're like, okay, so this will be x plus. It's always x minus. The difference is it's a 4 minus and a 4 plus. That's what changes. That's the mistake people make. Got that? So then as I work this through, my next step, I work through the negative. So it's x plus 3, as Jackson said. And then it's x what? Minus 4 plus 2i roots of 3. And then it's x minus 4. Okay, so we've got that. Always x minus. That's the fundamental theorem of algebra. It says that everything can be written in factored form with x minus the solution. That's how we start setting it up. Trust that. Okay, so here we are with our problem. A little bit different than the last one, huh? Okay, but good thing we're good at math. Just think if we weren't good at math, that would be Olivia, you can't give me a look like you're not good at math. You are good at math. You're good at math, Olivia. Okay, so we know that there's 3 terms here and there's 3 terms here. When you multiply 3 by 3's out, you're going to get a total of 9, right? Now here's the other thing. Do our resulting polynomials ever have an imaginary part to it? No, so all the imaginary parts should go away. If they don't, we probably did something wrong. So let's multiply this out. We'll start with the x, and we get x squared minus 4x minus, I'm going to write 2xi roots of 3. I'm going to put the x right after the 2. So I just finished with my first x. Everybody okay there? Now let's move on to the negative 4. So now I'm at the negative 4, and I'll get negative 4x plus 16 plus 8i roots of 3. Okay, still pretty ugly, but so am I. So we move on to the next one. Plus 2xi roots of 3 minus 8i roots of 3. Oh no, I got to do 2i roots of 3 times negative 2i roots of 3. What's 2 times negative 2? What's I times I? And what's root of 3 times root of 3? So I get positive 12. Wow. Hopefully we've got some good news that comes out here. What cancels? Yeah, it's like Christmas. It's like just start crossing it off. Yay! Boom, gone. It's the problem that keeps on giving, right? Just what? We did 2i roots 3 and negative 2i roots 3. Okay. So we've got x plus 3 times, we have an x squared. How many x's do we have? Negative 8x. So we're close. Like we did this back in 9th grade, right? It's Miss Kruger's class, right? Multiply each term by each term. So we got P of x is, let's multiply the x's. We get x cubed minus 8x squared. Combine like terms, x cubed hey, that took some sustained effort, didn't it? Did you know that I'm not making this stuff up. When you go through a sustained effort through a math problem where you're asked to pay like critical attention all the way through, you actually build more neurons in your brain. You actually get smart. You guys just got smarter. Yes, I took a graduate course this summer called Brain-Based Research in Mathematics. It was great. That's not true. That's all right. What? Where? Right now? We're done. We're done. Jessica wanted to go. Jessica wanted to check her answers, so she wanted to then write this in factored form. Jessica's wondering if we ran through the rational roots theorem, would we come up with these answers? Who's in for it? Who wants to go through and do it? All right, so just Jessica and I will run through it. Okay, the rest of you. Don't worry, Jessica. I'm there with you. Okay, I agree. Let's do it.